because for a lot of engineering students, we found that your soft skills point is always not high. So because now everything is online teaching and learning, I think you may take this opportunity to attend some of these, for example, workshop and so on, because this is all under online. You see Microsoft Teams. So, and also the time now is normally is not too long. For example, this is just 2 hours. So then you can earn your points. Okay. Some of you may ask, what is the benefit of this? There is no definite benefit, but at least if you earn this, you got extra strength that you can show to your future employer. Right? You have gone through all this training. So, for example, this is leadership. Right? There is emotional intelligence and teamwork skill and so on. So I think you should also receive. I just received this 3 minutes ago. Right? So this is a workshop. So then there is another one on the courses. Right? So they also provide all these courses. So you try to attend and earn the point. Besides earning the point, you can also get additional knowledge. You may or may not use. Okay, but I think business startup, all this is personal thinking style. I think is quite useful. Either you really going to do your own business or working, right? Because sometimes when you are working, you may also sometimes you have to think on behalf of your boss. So then you understand the reason behind. Right? So for example, now now sometimes you may have to think on the university condition. Okay? So we cannot simply allow you to come back. Okay. So now how many we have? Yesterday, I think yesterday our class we add in another 13 students. So now it hits 135. So at the moment I have only 105. Yes, there is a student raise hand. Anything you want to say? Alvin? Or just say hi. So the raise hand can be used to ask questions if you want. So Alvin Lim, do you want to say something? Okay, so beside this, so if you log into the eWeber, so now for LKCFES we are using EWBLE, so it's eWeber. Then you'll see that I already uploaded all the lecture notes, tutorial questions, and also the practical experiment sheet. So you can download it and have a look at it. Actually, maybe I have to show you this. So if you look at just a second. So if you look at the Microsoft Teams, okay, so you go to our own course. So I have created a lot of this channel. Okay, so when you are when you try to attend tutorials, so there's a group 1, group 2, group 3, and group 4. So you can go to the respective channel and then attend the class. So for the tutorial 1, Prof. Andy already prepared 3 videos for that. So it breaks into 3 sections here. tutorial 1A, 1B, and 1C. I already uploaded the video into the YouTube. Okay, so you can actually watch from there anytime. Okay, after that, next week onward, Prof. Andy will start the tutorial class. Okay, so practical will continue as what has been in your timetable. So we will start from week 3 onward. Right, so you just come according to your practical group. So in total, we have 8 practical groups. Okay. Oh, besides that, so one more thing to highlight to you is that in the general, if not mistaken, I share this. So Utah has provided the e-learning website. So if you want to know anything or you are having problems, this is a website you can actually visit. Okay? So there is a manual for you to use Microsoft Teams, scan documents, Weber, and so on. It's all there, so you can have a look. Okay? So we okay, so now how many we have? 118. Okay, so we will go into our lectures 1 now. Okay, so I will turn off my videos just to minimize the interference. Okay. So we'll go to the topic 1 now. So at the same time, let me start the recording as well. Okay, this start. Okay, so we started our recording. Okay, so we will start with our topic 1 here. So we start with the dynamic fundamental. This is actually extracted from your dynamic course, because I believe dynamic course is your year 1 subject, and some of you already written the knowledge to the lecturers. So we can have some quick revision, because we will be using this again. So we will start with this dynamic fundamental, then we will go to the linkages, introduction of the linkages. So let's see. Okay. So we will look at Newton law of motion. Okay. Maybe I activated my pen. Okay. So we will look at Newton law of motion. Okay. There is some technical issue now. Let me settle first. Sorry for that. Okay. My pen is not functioning. Okay, never mind. I skip my pen section, right? Okay, so we will start with this dynamic fundamental. We will start with the Newton law of motions, mass moment, and central of gravity, and then mass moment of inertia, or normally we call this second moment of mass. So then the parallel theorem, parallel axis theorem, so we call it transfer theorem, and then the center of precaution. So we will look at just a second. Okay, so we'll look at this rectangular component of velocity and accelerations. So this one, I think you've seen this before in the dynamics. So if we launch anything at a certain angle, so basically we can actually calculate the movement of this. For example, now this is a ball that is shoot out from this position O here. So we can calculate if we know the velocity and the angle, so we can know how high it will fly off and how far it will drop. So there are a few things or few assumptions we have to make of this motion of projectile. So first one is the acceleration at the x component, mean the horizontal component should be assumed as a 0. Right? So then the vertical acceleration, the vertical direction is governed by the gravity. Okay, so is minus g here. So this is gravitational. So normally we take it as a negative 9.81 meter per second square. And then the z direction, because we are dealing with if we draw it like this, so we normally assume this is two-dimensional problems. That's why the z directions, basically everything should be 0. So that's why az is 0. So then we must have some initial conditions. So in this case, under motion projectile, we set the launching position here. The O here is the origin. That's why x0, y0, and z0 will be 0. So then then we should have a Vx0 and Vy0. Mean Vx0 and Vy0 will have some value, but the Vz0 again will be 0 because of two-dimensional problems. So that's why in this case, basically we can ignore the z component because we are solving the two-dimensional problems. So by integrating the positions here twice, so basically we will get the Vx is Vx0, right? And then Vy will get it as a Vy0 minus GT, right? So if you can replace this as a acceleration, which is A. So some previously you may find in your notes in other subjects, they're also using this kinematics equation. Then you'll find that this is V y equal to Vy0 minus AT. So for this one, x we will have x is equal to Vx0 t, and then y is equal to Vy0 t minus half gt square. So again, for the z components will be 0. Okay. So in order to find the resultant velocity here, then we can use this formulas. V equal to square root of Vx plus Vy, right? So it means square of this plus square of the Vy, then you square root it, right? Add them together and square root it. So you will get this resultant velocity, right? So what are the angles? So we can calculate the angle because we have Vy and Vx here. So Vy over Vx we can find the angle using tangent relation. So similar things on the acceleration, we can also find the ax and ay, and we can find the actual acceleration. So you can see that these are the assumptions that we made. Okay, so I always emphasize to the student that everything we trying to solve using mathematical equation, there is always an assumption. Okay, so in this case, there is a tree here. So first one is a motion in horizontal direction is uniform. Okay, that's why our velocity is constant. So that's why our velocity is constant. That's why your acceleration is 0. That's why you say uniform. Okay. Motion in vertical direction is uniformly accelerated. Okay. That's why we have this gravitational effect here. So it's uniformly accelerated. And then motion of projectile could be replaced by two independent rectilinear motion. So it means we have x and a y, which is actually we are solving it independently. We can, right? So this is what we have for projectile. So next one we'll look at is the tangential and normal component. Okay, this will be very useful in our linkages. So please pay attention on this. So we learned this in dynamic as well. So when there is a particle move right, with a constant distance from a point C, okay, so then we will be able to find its relation between its velocity and acceleration. So the velocity vector given for the point P is V, or we can write it as a VET. So T is representing the tangential component. So it means that if the radius here is constant, so means the radius doesn't change, so there will be no normal component. Okay, so we only have a velocity and a tangential component. That's why you will find if you solve this problem under tangential and normal component, so basically you only have velocity, only have tangential component and no normal component. But when we go to acceleration, so it will be slightly different here, because now if you look at the acceleration vectors, right, so if we differentiate the velocity with respect to time, so basically we will get two component here. Right, so basically we will be getting a normal component and also the tangential component. So if you look at that, if you look at the derivation, I will not go one by one over here. So if we go all the way to the final at the bottom here, so you'll find out that the acceleration is equal to dv over dt at the tangential component, so which is this part. Okay, which is this part, at, right? So then, but the normal component will have this v square over rho. So basically the rho here is the radius of the rotation motion. Okay, so we have v square over rho as a normal component. Okay, that's why when you drive a car, okay, when you accelerate at the corner, right, so you will have this basically this cool component. That's why this component will contribute to you the centrifugal force, right? That's why if you are starting on the car making corners, so if you know the car friction value or friction force between the car and the road, so you can actually calculate how much velocity is allowed for you to make the turn safely. Okay, so this one is used in the racing, right? But for our normal car, normally we don't try to do that, right? Because on the normal road, right, the friction force is not constant for every corner, right? For example, if you go to Sepang F1 circuit, then that is possible because even their road is specially tiled and constructed. So then the value will be much more consistent compared to our normal road. Okay? So this is what we have. So A tangential and A normal. This will later lead us to, because if everyone know that the Newton's second law, one of the formulas we always use is F equal to ma. Right? So this will contribute to our force, the normal and the tangential component of the acceleration. Right? It will contribute to our force on our linkage when our linkage start to rotate. Okay? So even there is no acceleration, right? For example, now you drive your car without acceleration passing through the corners. Even though there is no acceleration, only your AT is 0, but you still have the A normal, right? The normal component. So now we look at one of the sample problems here. So we have a car making corners at 60 miles per hour at the distance of 2,500 feet. Okay. So some may ask why we are using miles and feet. So the reality is when you graduated, if you are working on the projects that under US and so on, so you may also you still have to work on miles, feet, and so on, and pound. Right? So it doesn't mean that Malaysia is using the SI unit. Your whole life will only deal with the SI unit. So sometimes it depends on the project as well. So you may actually experiencing that people give you all these imperial units. Okay. So the question here is a motorist is traveling on curved sections of highway at 60 miles per hour. So the motorist apply brakes causing the constant deceleration rate. So it means that there will be a deceleration at the tangential component. Knowing that after 8 seconds the speed has been reduced to 45 miles per hour. Okay, so determine the acceleration of the automobile immediately after the brakes applies. So for students, if you have any questions, you can raise your hand or even type in the chat. Because I'm using dual screen, so I will be able to monitor the chat column as well. Okay. Okay, so how are we going to solve it? So first we have to digest all the information. It given us 60 miles per hour. So we try to convert it to because our radius is in feet. So we can convert it to feet. It will become 88 feet per second. Okay. So this is the standard unit used in the imperial. So for SI unit, so we will be in kilometers per hour. That's why then we will set it to meter per second. There is more standard unit that we use to solve problems. So this is the initial velocity. Then is de-accelerate to 45 miles per hour. So it becomes 45 miles per hour. It's equivalent to 66 feet per second. Okay. So we can calculate the de-acceleration here. Right? So because of de-acceleration, your motion is counterclockwise. Okay. When you say de-acceleration, that's why your acceleration is clockwise. Okay. De-acceleration will be opposite the direction of the motion. Okay. So don't draw same direction with the motion. Then that will be acceleration instead of de-acceleration. Okay. So we can calculate the A tangential and A normal. So A tangential is just the acceleration. So we can take the initial, because it's de-acceleration, the final velocity minus the initial velocity divided by the times taken. Okay, so we have 66 minus 88 divided by the 8 second. So when they say deceleration, you also have to make sure that you get the value is negative. Okay, so negative 2.75 feet per second square. So for normal component, we have v square over rho. So v square is 88 feet. So we just take the initial value there divided by the radius of the turn is 2,500 feet. So we will get 3.1 feet per second square. Then we can find is resultant acceleration using this formula, square root of a tangential square plus a normal square. So when we have negative here, when we square, then there will be no impact to our final answer. So how you do it, you will still get the 4.14 feet per second square. So then we can also find out what is the actual direction of the acceleration at this point of time, A. So it's inverse tangents of A normal divided by A tangential, right? Because we specified the alpha is here. So we will get the A normal, which is this one, A normal divided by A tangential. Okay, I see one of your friend asked why are we considering the initial velocity instead of final velocity for this acceleration? Because that is because the problem started from there, right? We want to know the condition, the starting condition when you start to apply brakes. Okay, so because you are more interested on this process, the deceleration. Not after the acceleration, not after the deceleration. So that's why we take from the initial position there, right? Instead of after the deceleration. So that's why we take the 88 to solve the problems. Okay. Okay. So we will continue to the next one. So just now we are talking about the normal and tangential component. So beside that, we can also solve the problems of this angular motion, okay, or the rotational motion using the radial and angular component. So again, we have this diagram here. So now the P is again rotate, okay, at point O. Okay, so but this question then it will be slightly more complicated because now it gives us that the radius is changing. Okay, so you can see that if my P is at this point, so the distance from this point to the center of rotation is shorter. Okay, but when you go further, then the radius is longer. That's why our radius is also in the function of r er. So er is the radial component, right? It's a vector. So er actually no value. It's just representing the vector component. Okay. So for particle velocity vectors, so we can find the velocity is d over dt of RER. So it means that we will find the velocity by differentiating this formula RER. So when we differentiate it, then you'll find out that you will get two components now, right? So one of it is the changing in the radial direction. The other one is changing on the angular direction. So you'll find that the radial direction will become r dot because r dot is let me check. My pen really cannot use. That is too bad. Can I try this? Okay, never mind. Okay, so r dot, basically I can circle it. It's actually this one, dr over dt. So we call it r dot. Okay, so then for this component, So what we'll have this one. Right, so this one will become over here d theta over dt e theta. Okay. So that's why we have this r theta dot e theta. So e theta representing the angular component. So the value that we have is r theta dot. Okay. Those who I can see some actually attended the vibration class before. So this is what we have in the vibration r omega. Okay. So in vibration, they will call it a bit different symbols. So this angular velocity will become r theta dot. Okay. So similarly, if you look at the accelerations, then we have to differentiate the velocity with respect to time. So we will differentiate the basically this component. Okay, we will differentiate this component. Okay, why is still highlighted? So over here, we will differentiate it with respect to time. So then we will still get two components here. So as stated over here. Okay, so it become r double dot minus r theta dot square er. So this is the radial component, and then r theta double dot plus 2 r dot theta dot e theta. So this is the angular component. Okay, so you will have a radial acceleration and the angular acceleration. Okay, so that's why, because now the p is moving, okay, with the variation of the radius to the reference point. That's why the velocity now have two components. The acceleration also have two components. So the AR, or the radial acceleration, we will call it R double dot, which is the this one. Okay, this is R double dot. So minus R theta dot square, and then for angular component, so we have r theta double dot, or sometimes you will see that we call it r alpha. So I change it to pen. Now I can write. So sometimes we call it r alpha. Okay, instead of r theta double dot. Okay. So then the other one is 2r dot theta dot. Okay. So we look at another example here. So rotation of arm about O is defined by theta equal to 0.15 t squared, where theta is in radian and t is in second. So collar B, so this piece of slightly green color one is called collar B, slides along the arm such that the r is 0.9 minus 0.12 t squared. So now you can see that it gives you the r is in terms of function. So when it gives you this, means that this r will be changing according to time. Right? That's why we can also say this is r bracket t. Yeah? So means the r in the function of time. Okay? So after the arm has rotated about 30 degrees, so we want to determine the total velocity of the collars, the total acceleration of the collars, and the relative acceleration of the collar with respect to the arm. So now we can see that how we solve it. So we want to evaluate the time t for theta equal to 30 degrees. Right? So what we do here is that because it says 30 degrees, so we have this equation here, which is theta equal to 0.15 t squared. Maybe we go back. So that is a function given to you. The movement of the change of the position with respect to time. Okay. So we can substitute theta as 30 degrees, or then it's better we change to 0.24 524 radian. right? Because we always use radian to solve these problems. Then from here, you substitute in, you'll find your t is 1.869 seconds, right? So there's a time required. Then we can use the r function that is given. So r equal to 0.9 minus 0.12 t squared. So we can substitute the 1.869 into this formula, right? Into here, we substitute this t, okay? So we'll get r is 0.481. So if you want to find velocity, you just differentiate this with respect to time, okay? So you do dr over dt, then you'll get negative 0.24, because differentiate with respect to t, this will become 0. So we will left with this, okay? So we get negative 0.24 t. So again, you just substitute this 1.869 into the formula, so we'll get the velocity is minus 0.449. Then if we differentiate this again with respect to time, we will get the acceleration. So now acceleration is a constant value of negative 0.24 meter per second square. So this is r, so is a radius, so the unit will just in meter per second, and meter per second square. If we go to the angular component, so this is a formula given. So again, you substitute this 0.816, then you'll get 0.524, which should be same as here, because this is how we get the t. Okay. So then if we differentiate this formula with respect to time, so we will get the velocity function. So you substitute the t into the function, then you will get 0.561. So the unit will be radian per second, because this is angular movement. So if we differentiate this with respect to time again, then we'll get a constant angular acceleration of 0.3 radian per second square. So basically, once we get all this, so we can substitute into the formulas we have for VR, V theta, AR, and the A theta dot, right? So this is the things you have to substitute. So basically, then we can find the resultant, right, using the formulas and the respective angle, right? So it is always safe. It will be safe for you to draw the diagram. I think for this one, because we are interested on the velocity of this collar, so you draw this diagram. Then you also specify where is your angle. Okay. So because here you can see beta, you take it over here. So that's why the inverse tangents, you will take this component divided by this component. So you don't have to memorize this equation actually. You just sketch it out. So you know that this is the angular component. This is the radial component. Right? It goes this direction because of the minus. So that's why then you take this one over this one, and the inverse tangent, then you will get the angle here. Okay. So as long as you can draw this, then actually these formulas you don't have to purposely memorize which one over which one. Okay. So because if you do the other way and you draw your theta is over here, then I will mark you as correct as well. But if you don't draw this diagram, then you have to follow my marking scheme. Right? I'm using this, then you have to follow. Right? But if you draw your own, now you specify your beta is here, or I call another one. I call it maybe gamma. Right? So then you say your gamma is what? Is tangent inverse of, then you just say VR over V theta. So if you have diagram and the formula like this, so I will take it as a correct. Okay. But if you don't have diagram, you write this, then I have to base on my marking scheme. Then you will be getting the other side of angle. Okay. So for accelerations, you also use the formulas, just substitute the value. Okay. Then we will get the radial component and the tangential component. Okay, so again, we can find the resultant and the angle. Okay, so again, you can see that you sketch this. So it's always safe that you sketch out your component here, so that I know that your gamma is here. Okay, so you take this one, okay, the A theta over A R, okay, A theta over A R. So that is your gamma. Okay, so then you will get it right. Okay, so then we can find the relative motion. Motion of coral with respect to arm is a rectilinear and defined by the coordinate r. Right? The thing is, if we now consider the arm here or the bar here is stationary. So what happened to this collar? So this collar will only move with a velocity along the bar. Okay, because the angular motion is same as the bar. So when we say that collar B, the motion of collar B relative to the bar, then you only have the velocity. Okay, just like when you have two cars driving on the road at the same direction, so one driving at the 80 kilometer per hour, the other one 60 kilometer per hour, then you can find its relative velocity. Yeah, so it's about 20, means the car with the 80 kilometers is actually only 20 kilometers per hour faster than you. Okay, so this is relative motion. Maybe let me finish out this one, then we can end our class. So absolute and relative velocity in plane motion. So move to particle motion to this one we always call it rigid body motion. If you still remember in your dynamics, right? I can still remember some of the term used in the dynamic class because I taught dynamics, if not mistaken, about 7 or 8 years ago, right, in Utah. So now it's taught by other people, right, because I moved to teach the year 3 subjects, right. So this is rigid body motions, or we call it plane motions, right? So for example, this when I look at this diagram, I also think of this is a potato, right? So when these objects move freely, so for example, if I put a measurement at point A and point B, I will measure that the point A will have VA here, point B will have VB at this position. So in order for us to solve this, so because VA and VB are at different positions, so that's why then we can decompose it, and we can break it down to what we call it the translation motion and rotation motion. So we can take either VA or VB as a translation. Okay, so for this example, you take VA as a translation. So now we assume VA and VB has to move at the same velocity, right? But then we'll add it to another rotation motion. So we break it down. So since A is our reference for translation, right? So when we come to rotational motions, so means A will consider not moving, right? Because whatever motion has been described over here for point A. So now if you look at the relative motion between point B to point A, you only left with the rotation. Okay, so we can find the rotation here. So it's specified as a VBA. So if you look at the convention measurement here, VB relative to A point A, so means velocity at point B relative to point A. So this is how we write the wording there, VBA. Right? So if you do everything opposite, mean you take your translation, we follow VB first, right? Then when we come to the rotation, then you will have a VA relative to point B. Okay. So if we draw this in the vector diagram, so VB, we can find the VB. Yeah, VB is actually the VA plus the VBA. Okay, so that's why VA plus the VBA, then it will complete. Right, it will representing our VB. Okay, so mean we have this one. This is actually the actual velocity, but now we break it into two components. One is a VA here, one is a VBA here. So taking these three, you can draw the polygon here, and then we can find the value. Okay. So that's why this question, when I teach dynamic, I say that actually you can draw it using a scale polygon. You can still solve the problem. You not necessarily must work on the formula like this, because sometimes when we see formulas, we start to worry. Okay. So what is VBA? If you look at here, this is a tangential component, right? Because this is a fixed rotation point now. Okay. So tangential component is R omega, okay, or R theta dot, the one we see just now. So that's why this is R theta dot. So R omega. Right? That's why if we know the omega, then we know the distance between A and B, so we can find the relative velocity. Okay? So then we can plug in here. Right? So then we can find the VB. Okay? So just substitute this back into the upper equation here. So we will get this final equation here. What is the time now? So let me see how many slides before we end. I settle this slide because after this we will go for instantaneous center of rotation. So this one is still the same thing, but now you will see that sometimes you have to imagine because, for example, I pull the point A or cylinder A to the right, VBs must come down. Right? It cannot go up because this bar will not be elongated. So sometimes you have to think logically because sometimes questions only tell you VB going down. Okay? Then by logical thinking, VA must go here. Right? It cannot go the other side. Right? Because the bar will not be shortened. Right? So from here, then we can again choose either point B or point A to be your reference. So for this example, you choose point B as a reference. That's why you have the VB be a translation. Then since B has become a reference, so we will fix it here. So now we will just find the relative velocity with respect to point B. So again, you see, because we know VB is here, VB is here, VA is there, so we can build the polygon. Right? So we can actually build this formula as well. Right? We can build this formula, right, based on this one. Okay? So now again, we are looking at the bottom part here because the point A is the reference. Okay, sorry. So selecting point B as a reference point and solving the velocity VA of NA and angular velocity omega lead to an equivalent velocity triangles. So VAB has same magnitude but opposite sense of VBA. Right? So means either now we fix here, so we get this value. But if we fix here, you will get another value, same value, opposite direction. Okay? So angular velocity omega of the rod
in its rotation about B is the same as its rotation about A. Yeah? So angular velocity is not dependent on the choice of a reference point. Yeah? So this one you have to take note. Means this omega, it will be always the same. Either you choose point B or point A as your reference, your omega is still the same. Okay? That's why then your VAB or VBA is still same magnitude, right? But different maybe, but you will get opposite direction only, right? I think I shall end the class today because we only have 1 hour class. Any questions so far? So hopefully you can tahan for the online class for 1 hour. Okay. Tutorial should start on next week. Okay. I already informed Prof. Andy. Tutorial will start on next week. That's why he asked me to share the YouTube video first. So you can watch the YouTube videos. Then it will help you. So you can ask questions if you don't understand the video. Okay. So thank you very much. So again, I highlight again, if you have any questions, you can always PM me at the chat there. All right. So I will see you on next Monday. Okay. Thank you. Take care.